Today we're going to deal with moles, empirical molecular formulas, and combustion analysis if we have time. So essentially, there are two important conversion factors that are really important for these particular types of problems and for kind of chapter 3 and 1411. The first is that 1 mole is equal to the molar mass of a substance in grams. And of course the molar mass is something that you get from the periodic table. Okay? And the other is 1 mole is equal to 6.022 times 10 to the 23rd. Pretty much anything, actually. You can think of a mole as simply a number. It's like a dozen. If you have a dozen eggs, you have 12 eggs. If you have a dozen donuts, you have 12 donuts. A dozen people is 12 people. Same thing with a mole. A mole of atoms is 6.022 times 10 to the 23rd atoms. A mole of molecules is 6.02 times 10 to the 23rd molecules. And a mole of donuts is 6.02 times 10 to the 23rd donuts. So a mole is just simply a number, but it's really only a number that's useful for dealing with really, really small amounts. Because as you can imagine, well, let me give this as an example. If you had a mole of moles, like actually the little fuzzy animal, you basically have a planet that's bigger than Earth. Like that's how like it would actually have enough mass to form a planet that's about, bigger than Earth. So it's quite a lot. It's a huge, huge number. So so typically in chemistry, when we use this number mole, it's a mole of atoms or molecules. Okay, so like in the outline it says a mole is basically a chemist's dozen. A chemist's dozen. A mole is just another name given to this particular number, 6.02 times 10 to the 23rd. So you'll want to make sure that you know these particular conversion factors by heart. So that leaves us with another question. What exactly is molar mass? Molar mass refers to the mass of 1 mole of something. If you're given a chemical formula, how do you calculate molar mass? Well, let's do an example. So if you have a chemical formula for, say, aluminum sulfate, so that would be Al2SO4 3. Okay, so because I tend to be a little bit on the extreme side of organization, maybe borderline OCD, I have, I like to organize it like this. I think it makes sense and I think it makes it easier to follow. How many aluminums do we have here?
2.
In this formula? 2. So what we do is we take 2 times the molar mass that's given in your periodic table. Do you all have a periodic table with you? Yeah, let's go ahead and grab that. If you don't have a periodic table, well, I suppose I can run and get you one. Do you have one?
I can write it down.
Okay.
Right, yeah. Is this workshop day?
Yeah, it's workshop day.
Okay, I'm here.
All right.
I see you see it.
Okay.
No workshop.
All right. So you have 2 times the molar mass of aluminum, which if you're a nerd like me, you might actually have it memorized. But for most of you, we'll have to look at the periodic table. So 26.98 is the molar mass of aluminum, right? So then how many sulfurs do we have?
3.
3. Very good. And so sulfur has a molar mass of what?
32.
32.07, right? If you look at the periodic table, it should say like 32.07 roughly. And how many oxygens do we have?
16. 16.01.
How many?
16.
What did you say?
12?
12. There you go. I need some confident answers because I'm deaf and I can't hear.
16.
I thought she was
All right.
doing the next part, that's why.
So 16.00. So there are 12 oxygens, and each oxygen is 16 roughly. And if you look at the periodic table, that's its mass. So now what I do is I go ahead and multiply each of these and add them up. So 2 times 26.98 is going to be 53.96. 3 times 32.07 is going to be 96.21. And 12 times 16 is going to be 196. So 192. Mental math? Yeah, 192. Right? So then you simply add all these up and you should get 7, 1, 2, 4, 342.17, right? So this is the grams per mole. That is the molar mass. So now if this is the molar mass, so what is that good for? Well, molar mass allows you to convert from either grams to moles or moles to grams. Essentially, this number can be split up into what's might be referred to as its conversion factor form. Its conversion factor form might look like this. If you're starting with moles and you want to go to grams, then moles would have to come on the bottom. So I would say I have a mole of aluminum sulfate, and that is equal, 1 mole of aluminum sulfate is equal to 342.17 grams of aluminum sulfate. Okay? Alternatively, if you're starting with grams and you want to convert to moles, you may have 342.17 grams of aluminum sulfate on the bottom, and 1 mole on top. Right? So both of these are conversion factors that you could get from the molar mass, that you could use with the molar mass. All right, so let's go, now that we have an idea of molar mass and we have our 2 conversion factors that we're going to be using, let's take a look at some of these different mole conversions that we could end up having to use. Now, like for example, how many atoms are in 2.4 moles of boron? This is going to be a relatively simple one. You always start with what you're given, the 2.4 moles of boron. And we're going to go ahead and convert the moles to atoms. So what unit goes on the bottom?
Mole.
Moles of boron. And what goes on top? Atoms. So moles to atoms. And how many moles?
6.022.
What number goes on the bottom?
1.
1 mole. And how many atoms?
6.6.
6.022 times 10 to the 23rd. And then you simply multiply 2.4 times 6.022 times 10 to the 23rd. And what do you get?
1.4 to the power of 24.
I'm sorry?
1.4 to the power of 24.
1.4
times
times 10
to
to the
the
24th. Okay. Yeah, and since you started with 2 significant figures, your answer is going to have 2 significant figures. And this is going to go ahead and be atoms of boron. Now, and then it says how many moles are in 1.87 times 10 to the 25th molecules of sugar. So, in this case, 1.87 times 10 to the 25th molecules of sugar. It doesn't actually give us the formula, but we don't really need it actually. Because I'm just converting molecules to moles. What unit goes on the bottom?
Yeah.
Molecules, yep.
Okay.
And what unit's going to go on top?
Mole.
Moles. And what number? What number? Where do I put the numbers? What numbers do I put here?
Which more sugar?
1 on top. And what's on the bottom?
6.022.
6.022 times 10 to the 23rd. So, I just
Avogadro number.
multiply the top, divide by the bottom here, and I get what? I'm sorry?
31.1.
31.1. I'm trusting you're right. I actually don't have a calculator, double checking. So we're gonna assume that you are masterful at the calculator. Probably a safe assumption. Alright, so now, 31.1 moles of sugar. Okay, so, is that what all we're getting to?
Yeah.
Okay, cool. So that's how you do this. These are simple one-step conversions. Now, let's do something slightly more challenging. It says how many grams are in 7.89 moles of sodium chloride. Well, I am given 7.89 moles of sodium chloride. And I'm wanting to get grams. So what unit's gonna, yes?
No, the last one, I think it's 0.
Yeah?
I think it's 0.31.
I'm sorry?
I think it's 0.31. The last question.
Oh, no, it definitely should not be 0.31. Because this is 10 to the 25th. And if you divide 10 to the 25th by 23, 10 to the 23rd, you're gonna get 100. So it's going to be 100 times 1.87 divided by 6. I mean, I know that's going to be a fraction, but times 100, it should give you about 31. Yeah. It might be just that you end up switching a couple numbers in the calculator, but that can happen to anyone. So 7.89 moles of NaCl. What unit goes on the bottom here?
Mole. Mole.
Not number. What unit?
Mole.
Moles. Notice how I always emphasize putting the unit first? Most of the mistakes that I see from students who are doing conversions, either metric conversions or stoichiometry conversions with moles and grams and things like that, is because they try to put numbers in the conversion factors before they put the units. Never put numbers unless you have the units on both top and bottom. Because if you don't know what you're comparing, you don't know what numbers to put. So what unit goes on top?
Grams.
Grams. Alright, so what numbers do I put here? Where do I get my numbers for grams and moles?
So you put 1 mole.
1 mole, that's true, 1 mole. And what do I put for grams?
Just dip times.
Yeah, you have to add the molar masses of sodium and chlorine, because sodium and chlorine that's a compound, so we're going to have to add them up. Sodium, there's 1 sodium, so 1 times 22.99. And chlorine, there's 1 chlorine times its mass, which is 35.45. These masses are from the periodic table. And you get 22.99 plus 35.45. And you get 58.44. Okay? So 58.44 grams of NaCl is equal to 1 mole. So then I multiply the top, divide by the bottom. Of course, you don't really have to divide by 1, but 7.89 times 58.44, what do you get for your answer?
461.
461. And 3 significant figures is appropriate here, because you started with 3. All right, very good. So now let's do one that's just slightly more challenging. Number 4 says, how many molecules of H2O, water, are there in 35.8 grams of H2O? Oh, since I see some of you are still writing, funny story. As a joke, some students at a university, some chemistry students, they started a campaign, they launched a campaign to ban dihydrogen monoxide from campus. Of course, dihydrogen monoxide is H2O, water. And they put out all these like actual real statistics, like like so many thousands of people died from dihydrogen monoxide exposure, drowning, last year, and like all sorts of other like different things, and it's like stop the poison, etc., etc. And they put out this campaign, and like all sorts of students like thought they were serious, and they started like joining in the protest or whatever, and it actually like made the local news or whatever. It was really funny, but they took people into fighting for a ban against water. Anyway, so how many molecules of H2O are there in 35.8 grams of H2O? So let's take a look. There are 35.8 grams that it gives us. 35.8 grams of water. So what's our first step here? What are we going to do? I'm sorry?
So you have to mole
Grams,
over
moles.
grams.
Grams to moles. So what unit has to go on the bottom?
Grams.
Grams, yeah. Grams of water. And what goes on top?
Mole.
Moles. Now, how do I find the numbers to put here? What are the numbers I'm going to want to put here? 1 mole? Yeah. And then you said what?
Find the molar mass.
Find the molar mass of H2O, exactly. Now H is about 1, right? And oxygen is 16, so it's going to be 2 times 1, which is 2, plus 16, so that's 18. And I can put 18.02 to be a little bit more precise. That's not my final answer, right? Because it's asking me for what?
Molecules.
Molecule.
Molecules. So I have to keep going, don't I? What unit's going to go on the bottom now?
Mole.
Moles. And what's going to go on the top?
Molecules. Molecule.
Yeah. On the top, we're going to have molecules. So 1 mole is equal to 6.022 times 10 to the 23rd molecules of H2O. I know it's tempting to want to abbreviate the word molecules because it's kind of a long word, but don't use MOL for molecules because MOL is moles, right? I've seen actually students confuse themselves and accidentally start flipping things around because they use the abbreviation MOL for molecules. Alright, so then all you have to do now is multiply everything on top, divide by everything on bottom, and what do you get?
1.0 196.
So
37.
1.20.
Yeah, so
10
1.196 or 1.20 with appropriate sig figs times 10 to the
1025. 4.
24th. 24th molecules of H2O. Excellent. Okay. So you all have a pretty good understanding of this, I think. So let's break up and do some percent composition. So these are our mole conversions. We're going to go ahead and do some percent composition now. And then we'll switch gears and go back to empirical formula.
Mine? What? Did you mention about this one?
Not today.
Not today.
Yeah, some of that is related, but we're not going to get into using balanced equations quite yet.
No, I'm talking about this. This 4, the first 4. About the mole. It's a mole group.
I'm sorry?
That's not.
No, we're not doing that right now.
Okay.
Yeah, sorry. All right. So let's go ahead and determine the percent composition of ammonium nitrate. So I deliberately did not give you the formula for ammonium nitrate because I am evil. And I want you to prove to me that you still know how to write the name ionic and covalent compounds. What's the formula for ammonium nitrate?
NH4, NO3.
Oh, sorry. Let me raise your hands. I'll pick somebody. Too many people said one. Go.
I think it's NHNO3.
NHNO3 is a valiant effort, but not quite right.
Okay.
What is ammonium? Yes.
NH3 plus 1.
Yeah, NH4 is the +1, NO3 is the -1. So yes, NH4NO3, since the charges are balanced, NH4NO3 is the formula for ammonium nitrate. So we want to do percent composition. And if you use my overly organized way of calculating molar mass, percent composition actually becomes very easy. So let's be overly organized. How many nitrogen, first of all, what are the elements that we have present in this compound?
Nitrogen, hydrogen, oxygen.
Yeah, nitrogen, hydrogen, and oxygen. Now how many nitrogens do we have?
1. Oh, shoot, 2.
We have 2, right? So there are 2 nitrogens, and the molar mass of nitrogen is? 14.01, which gives you a total of 28.02. Now, how many hydrogens do we have? 4. And the molar mass of hydrogen is 1.01 approximately. So that's going to give us 4.04. And how many oxygens do we have? 3, yes. 3 times 16.00, which of course is 48. So now that we have calculated the mass attributable to each atom, we can add them up to get the overall molar mass, which happens to be 60.06. Wait,
I think it's 80.
that's not right.
80.
It's 80.06. What am I thinking? My mental calculator malfunctioned for a second, sorry. Alright, so now, here's what we're going to do. We are going to calculate percent composition. If I want to know the percent nitrogen, percent hydrogen, and percent oxygen in this compound, I'm going to take the mass attributable to each element and then divide it by the total mass times 100. So for example, if I want to calculate the percent nitrogen, I take the mass attributable to nitrogen, 28.02, divided by the total mass, which is 80.06, times 100%.
Excuse me.
And if I do that, what do I get? Bless you.
Thank you.
35.00%.
You got it already?
Yeah,
What is it?
35.00%.
35.00? Okay. Alright. So go ahead and do the same thing with hydrogen and oxygen. Tell me what you get. Now ideally these should add up to about 100, but depending on rounding, you might be off just a tiny little bit. In this case, there's an extra 0.01, but admittedly, I mean, close enough for government work, right? Alright, so we're good. Very good. So percent composition, pretty easy, right? Not bad. Do you want to try the other one on your own? Or do you want to skip ahead to empirical formula? What do you think?
Try this one off.
Want to try it? Okay, let's do it. Magnesium acetate. Go ahead. For magnesium acetate. All right. Let us see how you have done. Is anybody completely done? Nobody? Okay. Is anybody done with the first one?
Yeah, empty.
Okay. So, how many of you got the correct formula as Mg C2H3O2 2? Woo! At least 1, 2, 3. There we go. Alright, so now you got the molar mass and magnesium, there's one of them. 4 carbons times 12.01. 6 hydrogens times 1.01. And 4 oxygens. Whoops. Times 16.00. All right, 24.305, 48.04, 6.06, and 64.00. Add those up. Whoa, whoops. Little mistake there. Okay, 5, 0, 1, 4. 142.405. Did we get that for the molar mass? Good deal. Here's our grams per mole. Then 24.305 divided by 142, and this is our percent magnesium. 0.405. And then our carbon, carbon. That's a percent carbon, our percent hydrogen. 6.06 divided by 142, 0.405 times 100%. And then we have our percent oxygen. Wow. 64. 142.405 times 100%. Yay. So,
17.
did anybody get all these set up correctly, or at least as many of them as they could in the time? Good, good. So, several of you. Okay. Now, what did we get for our percents? What? Who got percent magnesium for me?
17.
What'd you say?
17.07.
17 point what?
17.07.
17.07. And technically your answer is more correct. Well, actually it would be 5 significant figures. That's okay though. That's close enough for government work, like I said. It's good. We're good.
Because I use 24.131 for magnesium. For
Yeah. Yeah, if you win 24.31, then you don't have 4. Yeah. So, depending on where you round your numbers, that will affect your significant figures. So, keep that in mind. And what about the percent carbon? What do we get?
33.6.
33.6. 4?
70.
You got 6,
73.
7?
No, 73.
33.73?
Yes, 33.73.
73.
Yes.
What did you get?
Well, I got 33.71, but that's because I did 48 divided by 142, my 37.
Ah, okay. So it's going to be close. We're going to say 33.73, but if you got pretty close to that, you're okay. Percent hydrogen, what do we get?
4.26.
Was that?
4.26.
4.26, thank you. Yeah, I really am kind of deaf, sorry. My apologies on that. Oxygen?
44.94.
44.94. Alright, excellent. So now that we know how to do percent composition, we know what percent composition comes from, and we also know how to do mole conversions, we're going to dive into something just a little bit more complicated, empirical formula. So let's go over empirical formula. Empirical formula is effectively the lowest whole number ratio. The lowest whole number ratio of atoms within a molecule. Now, using certain techniques such as mass spectroscopy and other types of experimental techniques, we can, and equipment, we can determine the percentage of each type of atom that might be present in a particular compound. But it doesn't necessarily give us the actual formula, at least not right away. We have to do a little calculation to make that happen. So in a case where, like, say, in a case where you would be given the percent composition for a substance and you wanted to figure out what the formula was, the empirical formula, what you could do is you could take the percent and assume that you have 100 grams, right? Because if you have 100 grams of something and it's, say, 50% carbon, that means you have 50 grams of carbon, right? So, assuming 100 grams turns our percents into grams. So let's take a look at this first problem. It says, determine the empirical formula for a compound that is 26.52% chromium. 26.52% chromium. And 24.52% sulfur. 24.52% sulfur. And 48.96% oxygen. 48.96% oxygen. So what we do is we take each of these substances. We take each of these substances, assume 100 grams. But see, different atoms weigh different amounts, right? And because different atoms weigh different amounts, we cannot use the mass ratios to figure out what the chemical formula is. However, mole refers to the numbers. Mole is directly proportional to the number of atoms. So, in effect, it actually represents the number of atoms. So a mole ratio would allow us to get the lowest whole number ratio. So I'm going to convert each of these grams into moles. So 26.52 grams of chromium, and to convert grams to moles, what would I have to do? What goes on the bottom? What unit? Grams. And on top?
Moles.
Moles. And the molar mass is?
52.00.
Yeah, basically 52.00. Chromium is one of those nice elements that has like a flat or kind of whole number molar mass. So then I would do the same thing for sulfur and oxygen. So I do 24.52 grams of sulfur. And I'm going to go ahead and convert grams of sulfur to moles of sulfur. 32.07 is the molar mass of sulfur. So that takes care of that. And then I'm going to do the same thing with oxygen. 48.96 grams of oxygen. And I'll convert grams of oxygen to moles of oxygen. 1 mole of oxygen, 16 grams of oxygen. So now, we simply calculate the number of moles of each type. How many moles of chromium do we end up getting? 2.10?
Oh, 8. I mean 5. 5101. That's what I got.
0.5101?
Yeah. Did anybody else get that?
That's about right. Yeah, it looks right. It looks about right.
Okay.
That what y'all got?
Yeah.
Okay. Now, that's the moles of chromium. How many moles of sulfur do we get?
0.7648.
0.7648. Thank you so much. And last but not least, oxygen. Don't leave me hanging.
3.06.
3 point what?
3.06.
3.06 what?
That's all I got. I think I might have did something wrong. That's
No, it does sound like about 3.06, but anybody got a fourth sig fig?
3.060.
3.060. There we go. Alright, it might have turned out to be exact, who knows? So here what we're going to do is, now that we have the moles of each one of these, this alone does not give us the ratio. What we can do to get the lowest whole number ratio of atoms is to divide each of these by the lowest number of moles. And the lowest number of moles of each of these is which one?
Chromium.
Chromium. So I divide this by, of course, if I divide this by 0.5101 moles, that gives me 1 chromium, right? And if I divide this by 0.5101 moles, what does that give me for sulfur?
About 1.5.
1.5 sulfurs. And if I divide this by 0.5101 moles, what does that give me?
6.
Like, what is it?
6.
6? About 6? Yeah, about 6.
We don't need an exact number in here, right? Because we just
Yeah, it's not going to be exact, but it should be close to exact, because there's always experimental error. You're going to get experimental error, and so it might be like, 5.98 or 5.96 or something. But if it's close to a whole number, you can usually put it as a whole number. Now, if it's a number like 1.67, you're not going to want to round it. Or if it's a number like 1.75, you're not going to round it. But if it's like 1.97, yeah, round it to a whole number. You're okay. All right. Can you have 1.5 atoms of sulfur?
Just multiply everything by 2.
Yeah. So since you can't have 1.5 atoms of sulfur, you're going to have to multiply everything by 2. So I'm going to multiply everything by 2, and that's going to give me times 2. It's 2 chromiums times 2, 3 sulfurs times 2, 12 oxygens. So if I write this formula out, then it's going to be chromium Cr2 S3O12. Which, if I know my polyatomic ions, wink, I might be able to surmise that this is really chromium sulfate. Make sense? But it's sufficient if you simply write your answer like this.
So you could write it either way.
You could write it either way. That is true. All right. So, how do you feel? Empirical formula. Not too bad? All right. Good, because it's about to get worse. All right. Let's do the next one. In experimental situations, you may not have a percent composition. You may actually end up weighing reactants and products. And so you may end up getting gram amounts to begin with. You still solve it in essentially the same way. So let's look at the second problem. It says that if you have 0.245 grams of powdered copper metal and you roast it in oxygen, heat it in oxygen, the product is weighed and found to be 0.304 grams. What is the empirical formula for this compound? Well, I see copper metal is roasted in oxygen, so I'm assuming that the elements that I'm dealing with here are copper, which is 0.245, right? And oxygen. But how much oxygen do I have?
Just minus the 3045, the 045.
Exactly. So this plus an unknown amount of oxygen forms some sort of copper-oxygen product, which is 0.304 grams of CuXOY. And I don't know what those numbers are. That's what I intend to find out. So I can calculate my grams of oxygen by taking my 0.304 grams of product minus my 0.245 grams of copper that I started with, and that will give me my grams of oxygen. How many grams of oxygen were added to the copper metal? Does that make sense? So this is going to give me about 0.59 or 0.059 grams of oxygen, I believe. You may want to check my mental math. My mental calculator hasn't been 100% accurate today. All right, so now we're going to go ahead and convert each of our grams to moles. So 0.245 grams of copper. And we'll do the same thing we did before, grams of copper on bottom, moles of copper on top. And that's going to be 63.55 grams of copper and 0.059 grams of oxygen. Grams of oxygen can be converted to moles as well. All right. So what do we get for our answers?
Oh wait, I did it wrong.
What was that again? Sorry.
I did it wrong, sorry.
That's what I got. It's 0.003855.
Ooh, that's a lot of significant figures. We had 3 to start with for the copper. How many? What should we have here?
1003885.
Basic.
0.00385 for the copper.
It's 386.
386
Yeah.
moles of copper. And how many moles of oxygen?
0.00369.
0.00369 moles of oxygen. Really? 0.00369?
Yeah.
I corrected.
That's crazy. Okay. So, if I divide each of these by the lower number, actually technically this should only be 2 sig figs, but we're going to run with it anyway. Divide both of them by the lower number, you get 0.00369 moles. That of course gives you 1 oxygen, right? And if you divide this by 0.00369 moles, what do you get? Point zero, wait, what?
Yeah.
1.046, okay. 1.05. Now, of course, this is coppers. This looks like 10. I'm going to just put 1. I'll put the oxygen over here. All right. With a 1.5 to 1 ratio, what can you probably assume?
Same.
Yeah, it's going to be about a 1 to 1 ratio. That this is effectively about 1 copper. So it's a 1 to 1 ratio, which means the formula for this compound is CuO. And I remember why I did that. It's because I wanted it to be off a little bit, because when you do this experiment in lab, you are not going to get a clean, perfect 1 to 1 or 2 to 1 ratio. chances are you're gonna get something like a 1.1 or, you know, a 1.1 to 1 or a 2.13 to 1 or something like that. And you're gonna be like, well, that's not very good. But in lab, especially if you're new to lab and your technique is not as sharp as it otherwise could be, you don't have the experience of a seasoned chemist, you're not going to get perfect results. And I don't want you to be disturbed by that. That's how you would take care of it. Does that make sense? Alright, so now these are empirical formulas, lowest whole number ratios, which is great for ionic compounds, but for molecular compounds, we want to know what the molecular formula is. We want to know how many atoms make up the molecule. See, there are no molecules in ionic compounds, right? They're just a kind of a continuous network array of positive and negative ions. But with molecular compounds, they actually do form these molecules, and the actual size of the molecules is important. And particular formula is important, because it gives us an idea as to its properties, and also how they can be separated. Large molecules can be separated more easily than small ones. So, let's look at a molecular formula problem. Now let's say that you had a combustion analysis that allowed you to determine the percent, or a combustion analysis that allowed you to determine the percent of hydrogen and the percent of carbon in the product, or in the substance that you were analyzing. And you came up with an empirical formula of CH. 1 carbon, 1 hydrogen, so 1-to-1 ratio. But you want to figure out the empirical formula. Well, in this problem it says, what is the molecular formula for a compound whose molar mass is 78.12? In mass spectrometry, in a mass spectroscopy, a mass spectrometer is capable of telling you what the molar mass of an unknown substance is. You inject an organic substance into it, and it knocks an electron off and fires it across a magnet, and based on how far it gets pushed, it determines the molar mass. More than you need to know for now, but it might be helpful for organic. Alright, but in essence it gives you the molar mass. But empirical formula analysis through like burning it and doing a combustion analysis gives you the empirical formula. So now we want to figure out, well, what is the molecular formula now that we have the empirical formula and the molar mass? Well, what you do here is you're going to take the empirical formula mass, and you're going to take the molar mass of the entire compound, and you're going to divide the molar mass by the empirical formula mass to determine a whole number multiplier. Because this is just some multiple of the empirical formula, right? This times 2, this times 3, this times 4, something. So, let's calculate the empirical formula mass. Carbon, hydrogen, that's 1 carbon times 12.01, right? And it's 1 hydrogen times 1.01. And it's 13.02 grams per formula mass, or per empirical formula mass. Grams per mole. So then all I have to do to calculate the molecular formula is to take the 78.12 grams per mole of the molar mass and divide it by 13.02 grams per mole of the empirical formula mass. I'm going to label it. Molecular mass divided by empirical formula mass. And what do you get? You said it, I think, right? What do you get as the number?
6.
Yeah, 6, right? So this is a 6. That means that the molecular formula has 6 times as many atoms as the empirical formula. So I multiply each of these by 6, and I get C6H6. Which this
Benzene.
is the molecule we call benzene. Cool. Well, we have finished up just in time. There are more complex empirical and molecular formula problems referred to as combustion analysis problems. I'm afraid we don't have time to get into that. This gives you the basic framework. Combustion analysis just adds a couple extra steps, but feel free to check out the videos on our website. There is another video on the website that covers combustion analysis under the video tutorial library 1411. And thank you very much for coming.